Okay, we're going to work through some examples here on impulse. So just a reminder that the formula for impulse, this is impulse. Again, we don't usually call it I. It's just force times change of time. This is impulse equals the change in momentum. Once again, impulse is the change in momentum, is something you want to understand. So to start with, I just want to refresh finding the change in momentum because we need to make sure we remember how to do that. Remember that change in momentum, change in anything, is its final minus its initial. So go ahead and try A first. We want to find its final momentum minus its initial. You just need to remember the formulas for momentum. Go ahead and give it a shot. Okay, what you needed to remember in this question, you might need to check this, is that, yes, again, we have mass of the object times its final velocity minus mass of the object times its initial velocity. In this case, V now stands for velocity and direction matters. So I hope you read this question and were very careful and saw that it changes directions. It initially is traveling west, and final, it travels east. So I'm going to go ahead. It doesn't matter which we call it. You should end up with the same change. I'm going to go ahead and call my initial negative and call my final positive. It doesn't matter. You could switch that. You will get the same answer. It just matters that if they're in opposite directions, one has to be positive, one has to be negative. So what we have here is the mass is 0.5. Its final velocity, now again, I'm calling the final one positive. So its final velocity is 30 minus its mass is again 0.5. And its initial velocity is negative 30 because I'm calling my initial negative. So either way, we should get the same change in momentum, or at least the same value altogether. Again, if we get a negative answer versus a positive answer, it's not going to matter in this case. We should get 0.5, let me see, 0.5 times 30 is 15, plus 15. We should get the same magnitude, right? This is going to give us a positive 15 as well. We take care of that double negative. So we should get the same magnitude of a change in momentum of 30 kilograms per meter per second. Again, if we get a negative, that just that aligns with our choices for what we chose as the negative direction. In this case, because we end up going a positive direction, that's a positive change in momentum. If I called my final negative, our answer here would be negative because we ended up going negative. So again, the magnitude will be the same. We don't need to worry about the signs as long as one is positive and one is negative. Did I do that right? No, that's right. Okay. And again, guys, also for this one, it's just a coincidence that the change in momentum happened to be 30. The individual momentums are 15. It has nothing to do with the fact that the speed was 30. This is the momentum. It's different things. Okay, so for B, an arrow of mass 0.2 kilograms is traveling east at 45 meters per second, then comes into contact with the target and stops. So go ahead and try the change in momentum. Again, P final minus P initial, subtract the two momentums, that's it. You just got to be careful which is the initial and which is the final. Go ahead and try it. Okay, so our change in momentum is P final minus P initial, which equals M velocity final minus M velocity initial. So initially, it is traveling east at 45 meters per second. I'm going to go ahead and call that positive. Then it comes into contact with the target and stops. So its final velocity is 0. So we've got its mass, 0.2 kilograms. Its final velocity is 0. Careful that we put the 0 there. Minus 0.2 times a positive 45. So we should have gotten 0.2 times 45. We have its change in momentum is negative 9 kilograms per meter per second. Now, that should again make sense. It lost all of its momentum, so its change was negative, right? Here, it still had speed. Yes, it came in with 15, it came away with 15, it still has speed, so it actually kind of gained some momentum. It just happened to gain its momentum in the opposite direction. Here, though, it lost all of its momentum because it came to a stop. So that should make sense. Go ahead and try this last one now. Okay, same as before. I'm going to go ahead and skip there right away. We're subtracting the two momentums from before and after. Originally, we have skating at a speed of 5 meters per second. So this is our initial speed. And receives a push from his dad, which increases his speed in the same direction. So I don't need to call these opposite signs. Again, with momentum, guys, direction is super important. These are the same direction. We can call both of them positive. So the mass is 20 times his final speed is 7 minus his mass is 20 times his final speed is 5. This is 140 minus 100, right? We should get a change in the momentum of positive 40 kilograms times meters per second, right? Yeah. So once more, again, this should make sense. He has gained momentum. This is an increase in momentum because he was going at 5 meters per second, and now he's going at 7. So this is a positive change in his momentum versus losing speed here. And again, this one happened to be a positive change in momentum because he came away with speed. Thanks. Because he came away with speed. So it's actually still a positive change in momentum. Okay, so we're going to have to do that in these questions. We're going to keep that in mind as we do example 2 here. So take a moment. You can get set up with this question, and then we'll talk. Okay, so you have a small sailboat, travels at 1 meters per second to the north on a lake. So I'm going to go ahead and draw that. I'm going to call this positive. This is the initial speed. A sudden gust of wind comes from behind and increases its speed to 3 meters per second in 4 seconds before the wind subsides. So now, this is the after. It increases its speed in the same direction, right? The wind is coming from behind and pushes it forward. So, once again, this is my final speed. They're headed in the same direction. They can stay the same sign. So we need to know what force the wind pushes with. So here's what we're going to use. We're going to use the impulse formula. Impulse formula is force times change in time equals the change in momentum. So all we're going to have to do is replace this, our change in momentum, with what we just did basically. And we are going to be able to solve for the force that the wind pushes with. So I want you to go ahead and go from here. I'm going to actually replace one more thing. We have P final minus P initial. This is mass times the final velocity minus mass times the initial velocity. We have everything we need. Go ahead and plug everything in. Solve for the force the wind is going to push with. Okay, let's see what we got. So force, the change in time is 4 seconds. Equals the mass of the sailboat is 700. Times its final speed, we said, is a positive 3 because the speed increased in the same direction, so we're leaving that positive, when initially it was only traveling at 1. So this gives us F times 4, which equals 700 times 2, so 1,400. Divide the 4 away. This is going to be the force the wind pushes with that entire 4 seconds. The wind is constantly pushing with this force for 4 seconds. So that's 1,400 divided by 4. So the wind is pushing with a force of 350 newtons. So that's how this formula works. We need to replace change in momentum with the individual momentums, the final minus the initial, and we go from there. It really doesn't get terribly much more difficult than this. We're not going to do any problems with angled vectors, so I'll give you that. The only thing you'll have to focus on is directions that are directly opposite each other. So you're not going to have angles, but you might have one pointing north and one pointing south, or one pointing east and one pointing west. You will have to pay attention to that. They will be opposite signs. Let's try this next one. So tennis players are taught to follow through with their serve. The idea behind this is that the follow through extends the amount of time that the ball and the racket are in contact. And that's good, right? We talked about how a big change in time causes a change in momentum. And we really want the momentum of that ball to change. So using a racket, this player can exert a 560 Newton force on a 57 gram, be careful with that conversion, tennis ball during her serve. Now what we're going to assume for this question is as the ball comes up, for the split second that it's at rest in the air is when it makes contact. So we don't need to make any assumptions about how fast the ball is going. We're going to assume right when the racket makes contact, the ball is at rest for that split second. So it says, at what speed does the ball leave her racket if the contact time is 0.0050 seconds? So once again, if you're reading a question and you see contact time and forces, guaranteed we're talking about impulse. I want you to try this. This is going to be, again, a situation where we have everything we need. We really just need to plug in. Once again, the ball is at rest to start. Go ahead and try it. Okay, so we have force times change of time. I'm going to go ahead and jump to the momentum formulas. Okay, we are looking at what speed does the ball leave her racket. So we're looking for velocity final, yep. And again, we are assuming that for that split second, the ball is at rest right as she makes contact. So we know the force that she can exert, 560 newtons. We know that the time of contact is very quick here, 0.005 equals the mass is going to be 0.057. Again, guys, careful with that. That's grams to kilograms. Move your decimal 3 times. Times, we want to know what speed it's going to leave with. Minus, just for the purpose of plugging in, I'll do this, but 0.057 times 0. It's at rest to start with. So all we got to do is solve. So we got 2.8 over here equals 0.057 final velocity. 0.0, that's a 5, 7. We've got a final velocity, 2.8 divided by 0.057, of 49 meters per second. 49.1, we could say. So that's moving pretty quick for a ball, yeah? So if she is able to exert that force, that's how fast the ball can leave her racket with this contact time. So again, what we just said is tennis players are trained to really try and follow through so that the ball is in contact with the racket as much as possible. So basically, if you can get a bigger contact time, you can actually exert less force and keep the same speed. That means you're having to use less energy, right? You're not going to get as tired as fast. So a greater contact time, less force with still the same speed. So that's what this question is saying. If instead her contact time was increased to 0.0065, we want to know if she maintained this speed, or in order to maintain this speed, I should say, how much less force would she have to exert? So we're going to find the new force And then we can say how much less force. So we're going to start here. And I want you to go ahead. We're using this as our final speed still. And now we're trying to find the new force. Go ahead and try it. Okay, so we have force times change in time, which equals mass times final velocity minus mass times initial velocity. That's our P final minus P initial. So again, what we're trying to find is the new force with this new time. So force times 0.0065 equals the mass of the ball is still 0.065, right? 0.057. Ah, crap. Oh, no, I did this right. I'm good. I'm good. Did I do it right? Okay. I can't read my own handwriting. That's a 0. Okay, I'm good. Going on from here. So the new time is 0.0065. The mass is still 0.057. And the speed, we want to keep the same speed, so 49.1. And once again, we could plug it in if we wanted to, but the ball is still at rest. So let's solve this here. We got 0.057 times 49.1. We got force times 0.0065 equals 2. I'm going to go ahead and write all of this because it's not many decimals here. 7987. We're going to divide that 0.0065 over. And we've got the force equals 430 newtons, 0.6, sure. So again, we can see that if this tennis player is able to increase their time, actually I needed one more step here. Instead of exerting 560 newtons, they would be able to exert 430. So to answer the question, we would subtract them to find how much less force she would have to exert. So she would have to exert 129.4 newtons less, this is our actual answer, than she would have if she can just increase that contact time a little bit more. She won't have to use as much energy and maybe last longer throughout the tennis match. So I hope this is making sense. You have one more problem you're going to do, and keep in mind that everything, it's working the same way. We're just solving for different variables, basically, from this equation. That's really all it's going to change here. So go ahead and try this last one completely on your own, being careful for the change in directions. Go ahead and try it. Okay, so a baseball is thrown at a speed of 30 meters per second. I'm going to go ahead and call that positive because it's the first one. Yeah. The batter then strikes the ball in such a way that it leaves the bat, which means it changes direction. Again, guys, we're not going to have any angled components here, but we will have things in opposite directions. You have to make a note of that. One of them has to be positive, one of them has to be negative. Determine the force the batter strikes with. Okay, so we're using impulse. Oh, wait. Oh, I need the time, don't I? Shoot. Let me go back. Okay. The batter strikes the ball in such a way that leaves the bat at 45. Strikes the ball in such a way. Okay, so with this question again, this next one here, same thing. Again, because we're dealing with contact time and force, that's your key, because I know some of you guys really struggle with knowing what formulas to use and when. It's based on what formulas have the variables they're talking about in the question. Sometimes it doesn't say, oh, hey, use the impulse formula, right? So you gotta be careful. Go ahead and try this one, being careful to note the directions of the ball. Go ahead and try it. Okay, so a baseball is thrown out at a speed of, I'm going to call this positive since it's the first velocity given to me. The batter strikes the ball in such a way that it leaves the bat at 40 meters per second in the opposite direction, right? The ball is thrown, he hits the ball and it travels the opposite direction. I need to call this negative. Be mindful of directions, guys. If they are opposite directions, one needs to be positive, one needs to be negative. And we have the contact time. So force times change in time equals our change in momentum. We are looking for F. So F times our change in time is 0.002. Our momentum was once again mass times velocity, final velocity, mass times initial velocity. So our final, being very careful with this. This was our initial, this was our final. So mass times negative 40 minus, let me plug the mass in, 0.0075. Let me just redo all of this. So we have 0.075 for the mass times its final velocity is negative 40 minus the mass is 0.075 times its initial was 30. So we got 0.075 times 40. That's 0.075 times 30. So we should get a change in momentum of negative 5.25. We have the force times 0.002. We divide by 0.002. And we've got that this equals, the force is 2,625 newtons. That's a lot, yeah, to hit a ball with. So when you guys try these, this assignment, again, really not very tricky with these ones. You're going to have most everything you need. You just got to pay attention to directions and be very careful where you plug stuff in.